Before we go into any more detail of these neural networks, I want to give you a brief example of how they actually work in practice. So, because it's topical, I'm going to talk about how we might use a neural network to determine which people should get the vaccine next and which people should wait a little bit longer. So we're going to be talking about vaccinations here. So maybe this is a bad idea because you're all sick of hearing about the virus already, but I think it makes a quite nice example. So what we will do, let's assume that everyone above the age of 70 has been vaccinated. We're going to consider all adults under the age of 70. And we're going to try to order them in the order that the neural network is going to decide they need the vaccine to get civilization back to normal in the quickest rate. Okay. So for every single adult in the country, we're going to create a three-dimensional vector. And the first dimension is going to be age. The second dimension is going to be, it's going to say, is there any underlying health condition with this person? So I'm just going to say health. And the third dimension is going to be their occupation or their job. So, for age, we're going to have people between the age of 70 and 18, as I said before. What we're going to do is something called normalization, where we just convert this age range into a more convenient range, which is somewhere between 0 and 1. So this 70 is going to be 1, and the range, this 18, is going to be 0. So halfway down here, we're going to have something like around about 45. That is going to be about 0.5. Okay? So we're just converting this range to a new range between 0 and 1. I'll talk about this a little bit more in the next lecture. For health conditions, we're just going to say it's going to be a 1 or a 0. Okay, so if they've got something relevant, like some cancer, asthma, diabetes, anything that could contribute to the seriousness of the disease, we're going to give them a 1. If they've got something that isn't relevant, or if they don't have any problems, then they're going to have a 0. So there's not going to be any in between there. And then job, we're just going to input as a teacher or, I don't know, lawyer, banker, whatever. And this will be encoded. You've talked a little bit about tabular data already, so you'll go through these label encodings, and maybe you'll end up with something like lawyer equals 0, teacher equals 1, etc. So we're just going to input the raw jobs. So, what are these hidden nodes going to represent? Now, bear in mind that we don't know this explicitly, but because this is an example, we can imagine just what the neural network is going to decide on. So a sensible thing that it might decide on is for H1, the first hidden intermediate step, to be something like the likelihood of hospitalization. So that's the wrong L. We're just going to say L, hospitalization. Okay, so this is the likelihood that we're going to get, that this person is going to be hospitalized because of coronavirus. The second one might instead be the likelihood that this person will catch coronavirus. And then finally, we're going to output this score y1, which we're going to say should be somewhere between 0 and 1. Okay, so quick note here, I have framed this as a regression problem just to make it a little bit simpler, a little bit easier on the eye. Most commonly when we use neural networks nowadays, we frame this as a classification problem. So you might have 5 nodes here instead. Let me change color. So you might have a y0, y1, y2, y3, y4, and or y1, y2, y3, y4, y5. And this would be like high severity. This would be medium high, medium, etc. I've just done it this way because it's a little bit easier to explain, but you can extrapolate from my explanation to the more common way that we use neural networks. So the only thing that we're missing now is to work out what the weights are going to be. And you can see, you already know that people who are older are more likely to be hospitalized. So there's probably a high correlation between this weight, this node, and this node. So we're going to give that a 1. However, it shouldn't make a difference how old you are to how likely you are to catch it. Maybe it does a little bit. I'm not that up to date on the biology research, but I'm just going to call this 0 to keep everything simplified. Again, with health, if you've got underlying health conditions, you're more likely to be hospitalized, but you're not necessarily more likely to catch it. And this way, it's the other way around. So based on your job, if you're a lawyer, or if you're someone like an IT technician that can work from home, then you're more likely to, you're less likely to catch it, but if you're a teacher, you're more likely to catch it. So this node depends heavily on X3, so we're going to give this a 1. But your job title, apart from your likelihood of catching it, shouldn't actually make any difference on the likelihood of being hospitalized. So we're going to give this a 0. And again, remember this is an oversimplistic example, so we're not considering things like the likelihood of transferring the disease once you catch it and the amount of people that you can transfer it to, or any of these more complex considerations. We're just boiling this down to the kind of bare bones variables that we might want to consider. So once we have these hidden representations, remember that this hidden representation, I don't really have a pink available to me, so I'm going to go for purple. This is going to be just a 2-dimensional feature, h1, h2, 2-dimensional vector, and from here we can say that both of these things are quite important. I don't want to get into any arguments on what's more important. This is what the press are doing already. The politicians are doing already. It's not for me to decide. I'm just going to say it's 0.5 and 0.5. So let's say we have an example where we've got a 70-year-old teacher with underlying health conditions. So he's a 70-year-old teacher with underlying health conditions. So the input vector for this person is going to be 1 because this 70 equates to 1, and then he's going to have 1 again. When we look at job now, things are a little bit more difficult because instead of having a convenient number, we've got teacher. I do want to just quickly, like very, very quickly, talk to you about how we'd actually get around this. Not going to go into detail here, but essentially, for each of the possibilities here, let's say we just have lawyer and teacher. We would, instead of having just one here for jobs, instead of having one node, we'd actually have another node, and this node would represent lawyer, this node would represent teacher. So instead, if this was a teacher, the representation would actually be 1, 1, and then this x3 would be, is the person a lawyer? It's no. And then the x4 is this person a teacher? The answer is yes, so it would be 1. And we can do that with infinitely many jobs. So if there's another one that's computer scientist, then this would now become 1, 1, 0, 1, 0, and we can keep going, just adding zeros down here. For this example, to keep everything simple, I am just going to say that we already know which jobs we're interested in. So we're going to say any job that has you in the public regularly, facing a large number of random people. We're going to give that a 1, and anything else is going to be a 0. So for example, a teacher is going to be 1, but a computer scientist or a student is going to be 0. So let's get rid of that. And we're just going to send this to 0, 1. I will just note, if you are going to do your projects on tabular data and you think you're going to need this thing where you add more nodes, the thing to start searching for is going to be called one-hot encoding. Okay, so teachers are going to be in this public-facing job, so they're going to get a 1 for this final feature x3. So our input is going to be 1, 1, 1. x1 is 1, x2 is 1, and x3 is 1. So I'm going to go to a different color. Let's take this one. Now we can work out what these hidden representations are. So remember, we have the weight W1 x1 plus W2 x2 plus W3 x3. So in this case, it's going to be 1 times 1, which is 1, plus 1 times 1, which is 1, plus 0 times 1, which is 0. So this is going to be 2. And here, for H2, we're going to do something similar, and we're going to get 0 from this way, plus 0 from this way, and then plus 1 from doing 1 times 1. So 0 plus 1 equals 1. So this hidden vector is going to be 2, 1. And then finally, we're going to multiply 2 by 0.5 plus 1 by 0.5. And so we do the exact same thing. So the weight 0.5 multiplied by H1 is going to be 0.5 times 2 plus 0.5 W2 plus H2, which is 1. So that's going to be 0.5 times 1, which equals 1 plus 0.5, 1.5. So now if we've got a 70-year-old who has asthma, who's a computer scientist or a lawyer, and this becomes 0, these two, the calculation for this is going to be the same, because this has now become 0, but this is going to become a 0, so this will become a 0. So for the second person, it's going to be 0.5 times the second person. We're going to have 2 0 now. So it's going to be 0.5 times 2 plus 0 times, 0.5 times 0, which equals 1. So they're going to get a lower score, which means that they'll be pushed a little bit further back in the queue. And we do this for all different possibilities of this input vector here. A couple of small comments that I want to add at this stage. For this y1, it doesn't actually matter that much if we map to between 0 and 1, because obviously 1.5 is going to be higher than 1. It's going to be, so typically you'd take all of your results and then convert things to between 1 and 0, the same way that we did for the age, but it doesn't actually matter that much in this case, because you're going to just get an output of 1.5 anyway. You're not doing anything additional with that. Secondly, I haven't talked about biases to keep things simple, but for example, if you thought that the importance of hospitalization was greater than the importance of the likelihood of someone catching it, and if you had lots of these output classes or output nodes rather than just the one, you could add a bias on here. So instead of it being x1 w1 plus x2 w2 plus x3 w3, you would just add on a bias. So maybe the bias for this one would be 1, and maybe the bias for H2 would be -1. And then you would get this one to be 3, and this one to be -1, in which case that impacts the results as well. So that's just something to consider. Not too important for this example. I don't want to overcomplicate things, but this is generally how neural networks work. So we've seen this WTX plus B equation, and that's y. And we've gone through that equation. So the next thing for me to show you is to explain how we actually learn these weights and these biases, which are here. So this isn't something that we're just going to put into the network ourselves. This is something that the network is going to learn by itself. And that's going to be the topic of the next part of this lecture.